Okay, thanks for inviting me. In this talk, I want to present some of the research we did in an ITEA project that finished last year, the MDENet project, where we applied model checking techniques in the context of digital twins. So let me first sketch a bit of the scenery here. We are working in the application domain of machine control. So we've got devices like factory production lines, metal printers, things like that, that are typically put in a factory. And if you look back 10, 20 years, then what you saw is that these devices are put in a factory and they just stand there in exactly the same way for years or even decades without getting any significant updates in the meantime. However, nowadays we see that these devices are more and more connected. So for instance, using 5G connections, etc. And this connected world allows for new possibilities. So you can, for instance, record exactly what is going on in the machine or in the factory. And maybe I should also turn on my video. And you can actually visualize and analyze the data that you have collected from this factory system. Not only does it allow you to collect this data, if you have this data available, you also want to analyze this data and see whether you can somehow improve the software that controls these machines. So based on what you learned, you can improve the software and then perhaps even do an over-the-air update of your factory system. Now, of course, if you do an update to either one machine or multiple machines in a production line, you do not want to you do not want your production line in the factory to come to a stop because you introduced a bug in the system. So whenever we do an update, we want to make sure that the update of the system is correct. So my focus in this talk will be on this on the verification of updates. Now, to zoom in a bit more on the context that we have, in this project, we focus on these machine control applications that are developed using a low-code UML-like model as essentially a single source of truth. So this low-code model does not only describe the control software that is deployed to the machine, but it also describes how the system is connected to user interfaces. It generates the necessary instrumentation to do this data storage and data collection. Even partners in the project have connected it to HoloLens applications, etc. And from this same single source of truth, we also generate model checking problems. So we can automatically generate a model checking problem from the low-code model and verify that its requirements are satisfied. Now, given the length of the talk, I am not going into all the technical details of the approach that we take here in order to do the model checking. Instead, I'll run you through an example and hope to give you an idea of what we can achieve using this approach. So the example is inspired by a real-world factory production line. So I took this picture last week, especially for this talk. What we see here are several hardware devices that are essentially connected into a production line. Now, I've got a running example here that is really similar to the machine that you see here, namely that of a production line that has a number of conveyor belts. So on both sides and on the front, there are some lifts that can raise and lower products, and there are two gantries that can pick up a product and move it to a different place in the system. So you can imagine that this is something that that could serve as a component in a production line in a factory. Now, as you can imagine, if you combine all these components, then you're looking at a realistic and a rather complex system. So for the sake of simplicity, I will zoom in on a single component that is buried deeper in this system. And that is a pneumatic cylinder that is used to drive the lifts in the system. So the pneumatic cylinder that I will use is essentially a piston that can be extended or retracted. It is connected to a valve, so we have an actuator that can either extend or retract it, and it has sensors that determine whether the piston is completely retracted, so that's the zero position sensor. And we have a sensor that determines whether it's completely extended, the end position sensor. Now, if you then look at how this low-code model looks, well, we are all familiar with UML diagrams, I assume. The static structure of such a low-code model in this setting is simply described using a class diagram. But it has some aspects that are specific to these machine control applications. So a class is, for instance, always a machine or a machine part, where the machine is the whole system you're trying to control and the machine parts are its components. So if you dive deeper into this, and I know this picture is not completely readable, what you see is that deeper down you get the conveyor belts, you get a gantry, and further down you get the cylinder. Now, within the class diagram, I already said we have this structure of machines and machine parts. Class members also have specific stereotypes. So we have inputs and outputs that are essentially the sensors and the actuators. Input signals and output signals are shared variables between the components, and variables, messages, and settings are things that are internal to a component. So this already gives you a pretty good idea of the interfaces that you have between the components and how the components are communicating with each other, but also with the environment in which the system operates. The class operations are commands that you can give either via a user interface or between different objects. So essentially, we only have one type of operations here. Now, the dynamic behavior, and that is then probably also no surprise, is described using UML state machine diagrams. And we here see an example from the cylinder model. So state machine diagrams here have states and transitions, and they can also refer to substate machines and subdiagrams. For instance, here we have a state disabled, which is the initial state, and we can take transitions to different states nested in enabled. For instance, the system can be either in the zero position, in the end position, or moving between these positions. Now, disabled is a substate machine, so we can zoom in a bit. Basically, disabled here describes what the cylinder should do if it is not currently operating. And essentially what happens here is that it checks, based on the current position of the hardware, what state in the state machine best corresponds to it. And this is further offloaded basically to this conditioning state. So conditioning here is a sub-diagram, which essentially is just a reference to another state machine diagram, which could explicitly be substituted here. So what you see here is a very elaborate if-then-else construct that looks at the input signals of the system and at the output signals, and based on that determines whether the system should be in the zero position or moving to the zero position, etc. So the idea is that if you switch it on, the system looks at the hardware, where is the cylinder, and then I move on to the state that best matches that configuration. As I said, we want to do formal verification of such models, and we take this low-code model that we could use to generate PLC code and deploy to the machine, or that we could simulate. Instead, we now take that low-code model and generate a formal model using the MSRL2 process algebra. And requirements in this setting are translated to temporal logic. In particular, since we are using MSRL2, it is the modal mu calculus that we use here. Now, the idea is that we take this formal model and this requirement, we feed it to the model checker, and hopefully, of course, the model checker says, yes, your requirements are satisfied. But of course, more often than not, the model checker says no, and we would like to get a counterexample from it. Now, what we did here in the development process was whenever we got a counterexample from the model checker, we try to correlate this with either the simulation, or we hooked it up to the debugger and tried to match the execution described by the counterexample in the control software. So that in the end, whenever we found a counterexample using the model checker, we were indeed able to replay that using the actual control software. So this establishes a general idea of how this low-code model is structured. Now let's very briefly look at some of the details in the translation. So the basis of the translation of the model to MSRL2 is fairly straightforward. We mainly need to describe how the states and transitions are translated, and how code on the transitions and inside these states is translated. The code is described using the structured text format for PLCs. So that involves a bit of work, but I think these are fairly standard translations for doing model checking of these sorts of systems. The interesting bit is how exactly are these low-code models executed on the hardware. So this took quite a bit of back and forth between us and also the developers of this low-code platform at Cordis to figure out that there is a cyclic execution model here where the objects and the state machines within the objects are executed in a predetermined order. And each state machine here executes at most one transition in every cycle. So figuring this out and embedding that in a formal semantics that you can translate to a model checking language is, I think, one of the bigger challenges here. Now, regarding the formulation of the requirements, I'm not going to show any detailed requirements here. I referred to an FMIX paper earlier in the presentation, and there are some examples of modal mu calculus formulas for requirements there. What we did instead, also to ease the life of the developers, is to come up with a set of generic requirements of which we think they should hold of every model. For instance, things like deadlock and lifelock freedom, but also sanity checks like every state in the system is reachable or every transition can potentially be executed. So these are essentially stronger versions taking into account semantic information that one would also check statically in such a low-code development platform. Now, basically, given also the time that I have, what I would like to do is show a very short video that takes the example of the cylinder model that I described and shows how we can find a live lock in that cylinder model. Now, what's interesting here is that this cylinder model is a standard example that is used in many systems. It's basically a default component that people reuse. And what we see here is that in this conditioning state that I showed before, there is a conditioning self loop. So there is a command. If the command conditioning is enabled, then the model will take the self loop transition. Now, if we verify the model and we select that we want to check for a live lock, then we offload this to msrel2, and it will come back saying that the verification failed and there is a counterexample. So in the current implementation, we still get a counterexample in the form of a labeled transition system, which contains exactly the transitions that are involved. So what we see here is that, I'm going to pause the video for a bit, is that we have a transition that goes from disabled wait for conditioning to disabled conditioning initial state. The command conditioning is put on the interface, and then somehow we keep looping here, and on this loop we continuously execute the transition from conditioning to the initial state of conditioning. Now, let me explain based on the state machine diagrams here what is going on. So on the one hand, in the particular state we are in, if we are in any substate of conditioning, this transition here, the self loop transition, is enabled if this command conditioning is active. Also, if we look inside conditioning, based on the structure of these if then else nodes here in this hierarchy, at least one transition is enabled. So we should be able to end up in one of these transitions. But according to the semantics, this transition, if it is enabled, takes priority over anything that is going on inside here. So the fix here is to somehow make sure that this command is only, or this transition is only triggered once, and it is not enabled continuously. So if you make that change, you can rerun the verification and indeed find that the requirements are satisfied. Now, wrapping up, I think this is a very nice example where you have a relatively simple component in a system like this that has been deployed for quite a number of years and that different people have looked at. And when doing the verification, we very quickly found this particular issue. And showing it to the developers with the counterexample, they were like, yes, this is evidently something that we need to fix in this model. So this really convinced the people at Cordis that this is something that we should take further, and also that should be offered to their customers. Now, I only showed very briefly, I'm using a very simple example, how we can model check such a low-code model. There are a couple of things in the setup that we have developed that I didn't show. For instance, we can now automatically translate the counterexample back to a format that is very close to the low-code models that the developer sees. We're also looking at scaling up the verification to larger systems. So right now, if we want to do end-to-end verification, we can only address smaller subsystems consisting of a couple of machine parts. We're currently using compositional verification and symbolic model checking to improve the scalability here. Orthogonally with a master student, working on supporting higher level verification languages. So, as I said, I did not cover any of the technical details in this talk, but if you're interested, then I am more than happy to explain some of the background in that as well. Thanks.